All right, maybe we can slowly get started. Welcome to the third session of Chapter 2 on predictive Bayes. So, we've already had a session introduction by me and a brilliant presentation by Sandra. And then today will be our third session. So, this is every 2 weeks. We're actually going to take a small break in 2 weeks. So, I'll mention that briefly. And as usual, I'd like to thank my fellow organizers, Professor Pia Aker, Jeremiah Snoblau, Jan, and Matthias for making things run so smoothly. So, we have a list of links as usual. There's the website, the mailing list that you can subscribe to, the calendar, etc. So it's just the same. Please feel free to share this widely. We still have one more chapter to go after we finish chapter 2. So a small bit of advertisement. Again, we're going to be having this satellite workshop soon. I think registration might be closed already, but if you're hanging around Singapore, then please do try to attend. A lot of us will be there, so you can actually meet a lot of the post-Bayesian community at the satellite workshop at BayesCon. And actually, a lot of us will be there in Singapore for the whole week, so you can always just email us if you'd like to, meet up for a coffee chat or something like that. Okay. So as usual for the post-Bayesian seminars, we do this kind of Q&A function in Zoom, but I don't really think people use that very often. So in the end, you can just either unmute yourself and raise your hand, or you can also kind of type questions in the Zoom, and I'll monitor that throughout the talk. Maybe I can let Vik decide if he'd rather take questions during or after the talk when we get started. So the structure of chapter 2 is shown here. We had Professor Sandra Fortini give a really nice theoretical introduction to predictive Bayes 2 weeks ago. And today we're going to have a session given by Vik. So he's going to be talking about predictive model selection and uncertainty. Vik is a PhD student at the University of Oxford under Professor Chris Holmes. I think he's very close to finishing his PhD, actually. And previously, he did his undergraduate and master's at UT Austin. So he had some overlap with Stephen Walker as well, which is how he made his entry into this kind of Bayesian field. Just a bit of a heads up, we're not actually going to have a session in 2 weeks because most of us will be away at BaseConf. So the next session with Professor Lorenzo Capello will be on July 1st. So it'll be in about a month. Okay, so I'm going to stop sharing my screen now and pass over the screen sharing to Vik.
Yeah, thank you, Edwin. Can everyone hear me all right?
Yeah.
Okay, fantastic. And the slides, that's all good as well? Okay, excellent. Yeah, as Edwin mentioned, I am entirely happy to take questions in the sort of likely event that I say something not entirely correctly. I'm happy to sort of entertain comments, corrections as we go. But yeah, this is just a bit of the work that I've been doing as part of my PhD, which is, knock on wood, very close to submission with Stephen Walker and Chris Holmes here at Oxford. Let me just try to get this camera going here. Okay, that's fine. All right. So as far as the sort of initial pitch, a bit of this early part will be sort of preaching to the converted for a little bit, I think. As Edwin and Sandra have already very well covered much of this ground in the last couple of sessions, but just for sort of a quick window or overview. When we talk about the sort of frequentist Bayesian divide in how we view uncertainty, I think the way that I have always really liked to motivate it and explain it to people is through this dichotomy, which again I'm sure you're all familiar with. The idea that frequentists see the parameter as something is fixed and the data is something which is random. And so we end up with these sort of repeated sampling interpretations of, if I ran this experiment several times, then so many percentage of the confidence intervals I build would contain the term mean. Whereas Bayesians see the data as something that's fixed and observed, and the parameter is something that's random and that we can make probability statements about. And the sort of mission, as far as I like to see it, of a certain kind of strain of this post-Bayesian work is to try and get the best of both of these worlds. Right? So uncertainty directly on a parameter somehow without having to interpret our results always through this repeated sampling, slightly contrived interpretation, but in a completely data-dependent framework that doesn't require some of these sort of often broken assumptions that we've spoken about in previous installments of this seminar, especially the specification of a prior specification of a precise model and so forth. And so in this outline, what we'll talk about a bit is I'll give a bit of sort of historical overview on Bayesian predictive model comparison methods, with a particular focus on sort of prequential view and scoring rules. Then give a bit of a refresher of the marginal posterior work, just insofar as it relates to the new work that we've done on extending that to model uncertainty. And looking at how we can think about questions of model uncertainty through the lens of predictive resampling, with a couple of hopefully thought-provoking and hopefully controversial demonstrations at the end. Okay, so to begin, I think we have this sort of going back many, many decades, even before this, emphasis on parameters as something which are, perhaps useful, but not necessarily the direct targets of inference, whereas observables are something that exist in reality and something that statistics should be more directly aiming to target. And I think the sort of baseline, which we'll come back to a few times in this section for a lot of this, is the work of Phil David on the prequential approach, and this idea that the purpose of statistical inference should be viewed as making predictive sequential probability forecasts rather than expressing everything just through the lens of parameters, and sort of looking at any statistical question as this sort of problem of, given a sequence of observed data in hand, how do we issue a probability forecast for the next observation? And so if we step back and think about this as like our statistical question, the immediate sort of next question is, suppose that I do have some model, and I begin to observe some data, right? X1, X2 starts walking in the door. How do I evaluate whether this model is doing any good? How do I evaluate these forecasts? And so sort of at a general level, you would use a scoring rule, right? And so a scoring rule is what it sounds like. It's just any kind of rule that is going to let me evaluate probability forecasts. For example, right, like very simple scoring rule, I could score 1 point if sort of the most likely guess, the mode of my predicted distribution is correct, and 0 points otherwise. This is, I mean, obviously not a meaningful scoring rule in like probabilistic terms, but just to give you this idea that a scoring rule as a general concept is nothing but a way to sort of evaluate probability forecasts as I name them. Okay. Now, the Bayesian marginal likelihood of any model, right? So the probability of the data given the model can be factorized out as sort of the product of the one step ahead predictive densities at each step. So under the model, what's the probability of my first point? What's the probability of my second point given the first one, the third one given the first two, et cetera, et cetera. And just a clever little trick of logarithms. If I log each side here, then we get a scoring rule, right? So this is a very nice little scoring rule for my data given some model, right? I just take the log probability of each point as it comes, and I add those up as I go. Right? Now, this doesn't necessarily have to be the scoring rule that you use, but as it turns out, this particular scoring rule has lots of very nice properties which have been studied in great detail. Right? The first is that it's prequential, following Phil David's work. It treats the data as if they arrive in sequence, which is, if you believe in sort of the forward arrow of time, then that's what happens in reality, right? We see the first data point, we evaluate it. We see the second data point, given the first data point, we evaluate that. We can evaluate our data and make our score sort of as we go without having to recalculate sort of on the whole data set at the end, something like that. It's proper, right? So it's a proper scoring rule in the sense that its expectation is maximized if we use the true distribution as our forecast. Like if we knew that there was some true distribution which was generating this data, and if we took that as our forecast in every time, then by sort of definition, we would get the best score on this performance. Right? There's no way that we can sort of game the system. If you think about my sort of 0-1 scoring rule from the previous slide, there are ways you could game that system. But in this case, we have a proper scoring rule. And then it's unique and guaranteeing coherent model evaluation. And there's this wonderful paper by Edwin and Chris sort of connecting this to cross-validation as a sort of grand unified theory of model evaluation. And so now we have this marginal likelihood. We have the idea of the marginal likelihood as a nice scoring rule. We know that the Bayes factor, right, our favorite Bayes factor for two models here is nothing but the ratio of two marginal likelihoods, right? The ratio of evidence between these two models. And so what that means is that, again, taking logs here, that the Bayes factor has an interpretation based on prequential scoring rules, right? So the log Bayes factor specifically is nothing but the difference in scores between two models using this nice prequential scoring rule where we're adding up the log probabilities of each step. And now to step even further back, right? Our favorite model selection rule, because we're all Bayesians, right, is the BIC. And the reason it's our favorite is because it has the word Bayesian in it. Well, no, actually, it's for reasons that will hopefully be sort of illustrated shortly, right? So with the BIC, we are sort of looking at the maximum log likelihood. We're penalizing that with some complexity based on the model. And we have these results that optimizing the BIC is asymptotically equivalent to optimizing the Bayes factor. And because of that, the BIC inherits sort of certain key properties of the Bayes factor, right? So specifically consistency, which is this idea that sort of as we observe more and more data, our probability of selecting the correct model will converge to 1. And so what we've done here is we started with this sort of very high level question of I have some model, I have some data, how do I evaluate whether my model is making coherent predictions? And we've gone to scoring rules. We've seen that the marginal likelihood is a very nice scoring rule. We've seen that the Bayes factor captures the marginal likelihood. And so somehow from this question, we've ended up at just me giving you a full-blown sales pitch for the BIC, for reasons which will become extremely clear shortly, right? And again, this is sort of something that's been studied in great detail, and we have sort of results looking at the consistency and the nice properties of the BIC from various angles, and kind of bringing together this idea that you can get consistency, broadly speaking, by maximizing the prequential likelihood with some kind of adjustment for the complexity of your model. That scales with the sort of size of the data that you're observing. Okay, so now to jump very quickly into martingale posteriors. As I'm sure this is scripture for many of us here. I won't belabor this too much, but I think there is one sort of particular point that I really want to try and emphasize to motivate what we do with model uncertainty. And so as you know, we have this idea of uncertainty coming from missing data, right? Which is something again that goes back as far as for example, this clip from 1965, saying an inference about finite population parameters can be interpreted as a predictive inference about the unsampled part of the finite population, right? So any statement that you make on a parameter has a sort of equivalent uncertainty interpretation if you slide it over as a statement about the data. And from this, you get the martingale posterior sort of framework or approach, the foundation of Bayesian inference being to try and assign a distribution on the missing observations conditional on what has been observed, right? And so we have this sort of flipping of the normal statistical viewpoint, where rather than observing some data, conducting inference on your parameters, and then retrieving your posterior predictive uncertainty over the missing data, we try to target the data directly, and then given sort of realizations of the complete population, we can try to back out our inference on the parameters or whatever it is that we're interested in. And we have this sort of general flexible predictive resampling pipeline where we use this sort of one step ahead bootstrapping kind of approach, simulate a new point, update the predicted distribution, and then continue this up to, in practice, some sort of sufficiently large number of iterations at which whatever quantity we're interested in has converged. Okay, and so this is the sort of demonstration that I do want to just briefly highlight here, is that we have this sort of demonstration of the equivalence between Bayesian parametric and predictive uncertainty when using like the normal posterior predictive in the original martingale posterior paper, right? And so we have this idea that if we have some likelihood in prior, then we get sort of this normal conjugate posterior predictive that everybody could, derive in their sleep. And then suppose we observe some data points, right? So n equals 10 in this case. And we're going to run this predictive resampling procedure. So we're going to use the posterior predictive to sample a new point, add that into our distribution, update the predictive, sample a new point, update the predictive, sample a new point, and so forth. Right? And we get here on the left this jellyfish plot, which is an official technical term. And what we see here is that each sort of sample path corresponds to one infinite population that we're resampling, right? So we all start at the observed posterior mean, but then as we sample forward, the different sort of sample paths converge to different population means, if you like, for that particular observed population. And then what we see is that the sort of kernel density over those resample populations is equivalent to the usual sort of conjugate posterior update that we would expect when we use sort of standard posterior predictive to resample our population. Okay. The thing I want to highlight here is if we think about the uncertainty that's being represented, right? What type of uncertainty is this? And so I would argue, right, that if you think about these different infinite populations that we're resampling, right, there are two components to your uncertainty decomposition, and at this point, some of you can probably see where I'm going, right? So this first one, this purple line, right, that corresponds to, if I just plot in this case the empirical variance of the theta bars across the different trials, right? So at the beginning, the empirical variance is zero because every trial starts at the same sort of theta bar, right? But then as I impute more and more data, I start to see some uncertainty propagation, some spread in sort of the mean of each individual sample path. And then the second one, this blue line here, is the model variance, and that's nothing but um, the variance in that posterior predictive update, which continues to shrink as n grows, and we sort of start to sample more and more precisely within each individual sample path. And those purple and blue lines add up to the black line at the top. And so what this very much reminds us of is aleatoric and epistemic uncertainty, right? And so we have this idea in the machine learning literature, these terms are kind of thrown around, they're used in a lot of different ways to mean a lot of different things. But the sort of one-shot explanation that I usually go for, right, is that aleatoric uncertainty is irreducible uncertainty, right? In a sense, it's uncertainty that comes from the data generating process or uncertainty that could not be reduced even if we had infinite data, right? And epistemic uncertainty is uncertainty that comes from the model, right? And that's reducible uncertainty. So our idea of epistemic is that that's uncertainty which, if I had infinite data, I could ultimately reduce to zero. And that's the same thing we see here, right? Is that the purple line corresponding to this aleatoric or irreducible uncertainty reflects sort of uncertainty in the data across these different infinite populations that I'm resampling, but the epistemic uncertainty, right, of my model kind of shrinks as I go forward, and those two can be combined to give me the total uncertainty, right? And in a sort of model selection sense, this is the same insight that we kind of apply here, which is that as I sample more and more data, right, the uncertainty in my model is, or the epistemic uncertainty is ultimately going to shrink. Okay, so jumping into the model uncertainty work, I would assume that I'll be interrupted if there are any questions, unless I'm missing something from the chat. Okay. All right. So when we think about model uncertainty, the sort of framing of it that I really like comes from this 1995 work of Draper. He says, think about your model, right, as consisting of two things. One is your structural assumptions, right? And so an easy sort of familiar example for that is the link function in a GLM, right? And then two is your parameters theta, and the parameters depend on the structural assumptions, right? So like the coefficients that I have in a GLM are interpreted in the context of what link function and what sort of response distribution I'm assuming. And then we have this clip here. A widely used approach involves enlisting the aid of X, the observed data, to specify a plausible single best choice S star for S, and then proceeding as if S star were known to be correct. In general, this approach fails to assess and propagate structural uncertainty and may lead to miscalibrated uncertainty assessments, right? And so this is saying just that usually what we'll do is sort of say, okay, this is the structure I'm using, and then assume that all the other uncertainty follows from that. What I'm giving you here is nothing but, again, another sales pitch for sort of standard Bayesian model averaging, right? What he's pointing out here is the normal approach, so to speak, where we try to calculate the Bayesian uncertainty on some quantity of interest C. That corresponds to nothing but assigning sort of a point mass of 1 to some model, M star, that we're assuming is correct. And if we do the sort of, standard thing that's seen, at least in a lot of the applied literature, of saying, okay, we're going to select our model with AIC, BIC, cross-validation, whatever model selection method that we like. And then we're going to use that model, and then we're going to do the uncertainty, right? This corresponds to sort of implicitly having that model M star in our uncertainty calculation, but assigning it a point mass of 1. The Bayesian model averaging argument is that we should allow for the possibility of different models, but we should again sort of assign those models uncertainty weights based on marginal likelihood or the probability that we think each one is correct. And in a lot of kind of real world predictive scenarios or applications, this is shown to really help with your robustness and quality of results and so forth. And so then the question comes, where do we get the weights, right? It's like, how do we calculate these uncertainties on the different models? And so, existing approaches like such as the Bayes factor share a number of common concerns, and sort of over the years, there have been hundreds of efforts to sort of redefine different versions of things such as the Bayes factor that are attempting to address these in different ways. Sort of, setting objective priors to your Bayes factor, or using the data to sort of inform what those priors might be, et cetera, et cetera. But we sort of approach this from the missing data framework, right? From the martingale-posterior framework, where we say uncertainty comes from missing data. And in the sort of initial literature, we have this idea that we should flip the order of inference, right? And we should figure out our parameters as a function of the data. And so what we say here is, what if we just say that that's the model, right? So rather than sort of using the observed data to conduct inference on our models and then look at posterior predictive uncertainty, what if we first try to directly target uncertainty on the data, and then we use those different sort of replicates of the infinite population to figure out our weights on the different models. And the resampling pipeline looks much the same, right? So what we do is that we, at our sort of initial observed data, right, we select the best model. I'm going to leave best intentionally vague for now, but if you were paying attention earlier, you might know what I'm going to say about that. We select the best model, we simulate a new data point from that model. We impute that into our population, we update our choice of best model, and then we repeat this predictive resampling procedure until we've sampled some sufficiently large amount of data for our choice of the best model to converge. And then if we repeat this over several Monte Carlo iterations, then we get uncertainty on the model selection. So how do I select the best model? As I was saying earlier, right, we argue that the key here is that you need a model selection criterion which is consistent, right? Precisely because we're framing this entire thing through the idea of, as I procure or as I see what the infinite data looks like, I'm going to select the correct model. And so based on what we said earlier about sort of coherent and optimal predictive model comparison, we use the BIC for that, right? Which, as you sort of sample more and more data, has this sort of nice built-in trade-off between the complexity of the model that you're choosing and the fit to the observed data. Another way that you can sort of think of this is that the model selection criterion, in this case the BIC, which is consistent through this resampling procedure, is converted directly into posterior probabilities, or a measure of uncertainty over the different choices of model data. I think that this is perhaps best explained with an illustration. So I'll give you one here from density estimation, right? So this is a very sort of standard model uncertainty question, right? If I'm modeling these points with a Gaussian mixture, sort of mean, standard deviation, normally distributed clusters, then how many clusters should I use? How many components should I use? The sort of traditional approach would be compare a few different things with AIC, BIC, and then just pick one. But if we're looking at this from a sort of predictive resampling approach, what we say is take my observed data, right? Make several replications of the observed data, fit sort of your optimal model, in this case using BIC, and then predict a new point from that fitted model with the optimal BIC and with some sort of maximized parameters for the mean, standard deviation, et cetera. Then sample a new point from that model, refit the model, sample a new point, and repeat this recursive procedure and so forth to get uncertainty over the number of components. And so what we'll see here is a quick animation where the initial fit, right, the sort of initial best model, I believe has one component, but then we sample a new point from that, which is different across different replications of the population, and then we start to see the uncertainty propagate from there, where certain models end up with more clusters, certain models are made of one cluster. As we sort of sample new data from the fitted models at each step, we propagate uncertainty through the resampling of the data. And in this case, it's just 4, but if we repeat this over sort of several Monte Carlo iterations, then we get our measure of uncertainty over the number of components. So in this case, some of them ended up at 3, 2, 1, and so forth. Okay. So that's a quick demonstration on density estimation. I think perhaps the more interesting demonstration, and perhaps one where we'll hopefully have some questions, is hypothesis testing. Right. So same thing with hypothesis testing is that traditionally we have this sort of interpretation where frequentist hypothesis testing depends on this idea of repeated sampling, right? If I ran this experiment several times, then I'd expect to reject the null hypothesis only 1 minus alpha% of the time when it's actually true. And Bayesian hypothesis testing has often this kind of inbuilt dependence on some kind of prior, which then allows me to calculate a posterior probability of the hypotheses relative to each other. But in our sort of in our predictive resampling world, what we say is let's target the data directly, right? So for a simple kind of point hypothesis demonstration, suppose that our null hypothesis is just this model theta equals 0, and our alternate hypothesis is theta equals 0.1, right? And then suppose we observe some data. What I'm going to do here is that, since neither of these models, or since these models have the same number of dimensions, I can kind of ignore the dimensionality part of the BIC and just maximize the likelihood directly. And so what I'm going to say is that I'll observe some data. If the likelihood of H0 or H1 is higher, I'm going to generate my next data point from that hypothesis with my known variance of 1, and then I'm going to repeat that over several replications of the population to ultimately get my uncertainty on 2 hypotheses. And the result is something like this, right? So we start at the observed sample mean here, which I believe in this case was just above 0.05. So H1 is sort of true hypothesis initially. But as I sample and impute more and more points, we get this similar jellyfish plot, but where we ultimately get this clear separation at this decision boundary of 0.05 between populations that correspond to the null hypothesis and populations that correspond to the alternate hypothesis. And so what we see here is this sort of Nyman-Pearson interpretation, right? Where we have this idea that hypothesis testing is ultimately a decision rule on some summary statistic of the complete population. And there are sort of certain critical regions of the population where the null or where the alternate hypothesis would be preferred. And through this resampling procedure, what we're trying to do is get a sort of probabilistic measure of which of those regions our initial population falls into. If we go to a two-sided hypothesis demonstration, right? So now suppose I'm looking at a binomial proportion parameter. My null hypothesis is 0.5, and my alternate hypothesis is theta does not equal 0.5, right? And so I actually have a cute little demonstration here. So suppose that I run a survey and I observe 168, in this case, oranges and 132 green apples out of 300 total, right? And I am now trying to test these 2 hypotheses against each other, right? Is there a significantly different number of oranges and apples? The frequentist interpretation, right, would be if the null hypothesis is true, right? So if, in fact, theta does equal 0.5, then how extreme would this result be if I were to sort of repeat this experiment of sampling 300 total fruits several times? And so if the true split is 50-50, right, then this plot shows the likelihood of different results between about 100 and 200 apples and oranges. And the chance of getting 168 oranges or more would be 2.15%, right? So that's the likelihood that I get a result which is as or more extreme as what I did in fact observe. right? And so the frequentist would say, sort of, if this is less than 2.5% if you're doing a two-sided test, or 5% if you're doing a one-sided test, then I reject the null hypothesis because what I've seen is sort of too extreme to have been generated by chance. The Bayesian would say, what is the evidence for each hypothesis given the observed data, right? And so if the true split is in fact 50-50, same as before, the chance that I observe 168 oranges is 0.53%. If the true split could be anything, right? So it's just something between 0 and 1, my true theta, right? The chance that I observe exactly 168 oranges is 0.33%. And now some of you can again probably see where I'm going with this, right? Which is that the Bayesian now has seen that actually there's greater evidence for the null hypothesis than the alternate hypothesis, because the ratio of these values is sort of larger than 50%. And this sort of, very, very well reviewed result is called the Linley-Bartlett paradox, right? And sort of one way to view this is that the paradox comes from the prior, right? Because what we've implicitly assumed here is equal prior mass on the two hypotheses, right? So in the null hypothesis, we've assumed sort of a prior mass of 0.5 on this one value. But in the alternate hypothesis, we've taken this prior mass of 0.5 and we've diffused it across the entire real line between 0 and 1. And so it makes sense that we would be more likely to prefer something coming from the null hypothesis. If we now think about this from the predictive resampling idea, right? We are looking at this as something where we're trying to fill in the missing fruits based on the BIC. So if my likelihood is maximized at theta equals, that should be 0.5 at the bottom, and there's no dimensionality penalty because that's sort of a fixed model, then I'm going to generate my next data point from a Bernoulli with just half and half probabilities. If my likelihood is, however, maximized at the observed, in this case, the likelihood would be maximized at the observed mean of what I actually see, right? So initially it would be 168 over 300 probability of an orange. But now that I'm allowing that degree of freedom, I have a dimension penalty of 1 on the BIC calculation for the model. But if that's preferred, then I'm going to generate my new point from a Bernoulli with that as my sort of observed sample mean. And so we sort of visualize this, right? In the first case, the null hypothesis is preferred, right? So this is just slightly favors the BIC with the fixed sort of parameter of 0.5. But then I generate a new point from that. Suppose it's in fact an orange. I did in fact sort of rig these numbers a little bit so that that becomes the point where you would flip to the alternate hypothesis, right? At that point, it's just slightly too extreme and the BIC prefers the model with the floating parameter. And so now I'm going to use my alternate hypothesis to fit the next point. And I'm going to repeat this on and on and on until I converge to one of the two hypotheses. And I replicate that over several different realizations of this infinite population, right? Alternating between observing the data, comparing the models, then sampling the data, comparing the models, sampling the data again. And ultimately, I'm going to sort of take the probabilities at the end as my sort of posterior probabilities of the two models. And so I get this result, and like the sort of final posterior probabilities are about 77% for the null and 23% for the alternative. But what I'm going to argue is that these results have a completely prior-free interpretation in terms of posterior uncertainty on the two hypotheses. And also that we can accumulate evidence in favor of the null hypothesis, unlike what you would usually be able to do in a frequentist sense, where you can only ever reject the null hypothesis. And so, yeah, I don't expect everybody to agree with these statements, but I would argue that this sort of gives you a way of bridging the gap between frequentist and Bayesian hypothesis testing. Okay, that is all I have. I have the QR code of the paper here, which is up on archive, but I am happy to take any questions.
Thank you so much for that excellent talk. We can open the floor maybe to any questions. So if you have any questions in the audience, please feel free to unmute and just ask away. So while people are pondering, maybe I'll start with my first question. I was looking when you discussed this notion of doing model selection with the BIC, is there a sense that the marginal posterior distribution on your parameter is now kind of Bayesian model averaged, like kind of, the usual integral over like P of the model? Like, is it actually exactly that object now?
Yeah, I think so. I think that we discussed this a bit with Stephen as well, and we have this kind of idea that like if you were to take sort of the Bayesian model average as your like sort of predictive distribution at each point, then you would recover the Bayesian model average, if that makes any sense. And so, right, so like somehow you could view this as a generalization of that, where that's sort of the fixed point where you would get the same thing out, sort of marginalized through this predictive procedure.
Mhm. 'Cause then there is indeed extra uncertainty now in which model you're choosing to predict. So I presume that the variance for any parameters would be kind of larger than if you just used a single model, right? So I guess it is kind of like Bayesian model averaging. It's quite interesting.
Yeah. And I think there was in the sort of the Phil David paper from 92 on stochastic complexity, which I showed at the end of the BIC section. There's an interesting comment there which got me thinking recently about sort of the idea of like how quickly even with the BIC, sort of how quickly do you trade off between sampling data and finding the right model? Because initially,
Yeah.
right, the sort of speed at which you need to like optimize the parameters within the BIC might still not necessarily be enough to sort of make up for the complexity of the different models. Perhaps that's not making any sense, but the point is, I think that that's something that still we need to still study. In terms of like looking at in practice the sort of rate at which the parameter optimization works.
Thank you. That's super helpful. Any other questions from the audience?
There's
Hey,
one in
Vik,
the
that
room
was
here. Oh, sorry. You go ahead.
just that was very cool, very interesting. Thank you. Maybe just I guess I'm kind of taking your bait ever so slightly on the final example. If I remember correctly, the BIC is an approximation of the is a Laplace approximation of the marginal likelihood under uniform priors, I think. So by using the BIC, are you somewhat using a uniform prior anyway?
Yeah, I think what Chris would want me to say is that you can always sort of find an implicit prior if you want to, but um, that comes from again kind of like the pre-Bayesian approach of like viewing the prior as fundamental to the calculation. So I mean I think that that's sort of a non-answer to your question. I think probably, but I would argue that sort of that's not critical to the calculation of the interpretation.
And I guess if it behaves differently, then it's not right. So if you don't get the Linley-Bartlett paradox, which you would have got under a uniform prior, then I guess it must be doing something different.
Mhm.
Cool, thanks.
Yeah, thank you.
And you mentioned there was a question in the room, so maybe we can take that now as well.
So on the last slide, the thing that you're showing, is this a martingale on the parameter on the like which hypothesis it is still or not anymore?
Um, hmm. So I mentioned earlier the sort of idea of the convergence coming from martingales. I mean, that's in reference to the sort of the convergence of the model selection being sort of a bounded super martingale, right? And so like as you observe more and more data, you're going to converge to like selecting a single model. Now you're talking about the choice of hypothesis, right? I don't know. I like I imagine I imagine that it would be, but I haven't actually sort of written this down, so to speak. As far as like what's the martingale here? Yeah.
But would the ones like the probabilities that you get after converging, are they different to the probabilities that you get after one step for the two different hypotheses? This is maybe the like you could just go one step ahead, simulate one data, then pick a hypothesis.
Mhm.
But in your example, this would be probably 50-50, right? Because if I understand right, if you sample an apple, you will get hypothesis one, and in the other case, hypothesis zero.
Yeah.
But the limiting probability is actually differ in this case, right? From the one step probabilities, or
Yes, okay, I see what you mean. And yeah, I think that actually, I think it does connect back to the earlier question about sort of like the parameter optimization within the BIC calculation, right? Because where that's coming from is sort of whether, you know, how you like optimize the parameters
Yeah.
within the model.
yeah.
So I can't sort of come up with a witty comment about it off the top of my head right now, but I think that there's a connection there. Yeah. Mhm.
I can go again if nobody else wants to, but I'm happy to keep quiet if there's more interesting questions. I wondered, have you thought about what happens? I'm thinking maybe you're testing a hypothesis, say you're doing linear regression, you're testing a hypothesis whether one of the parameters is zero. What happens as P gets very big, and maybe the number of observations doesn't get very big? Do you think that you can still use this same paradigm? Because that's a sort of situation I'm thinking where you think about needing a prior. And I wonder, can you still, yeah, can maybe you don't.
Yeah, I'm not sorry. So could you repeat that again? As P, you mean like the number of
The number of
dimensions?
regressors. So I'm doing linear regression, and the
Yeah.
number of regressors gets big. Maybe it doesn't go to infinity, but it's big relative to the number of observations I have, and I want to test the hypothesis that one of the parameters is zero.
Mhm. Yeah, I think that because I
Maybe it's
suppose the
still okay
rest
because
of
you're using the
the
BIC. I don't know.
I mean, I think that so we have some sort of variable selection demonstrations in the paper as well. I think that it maybe does come back to the same question about kind of optimization within the model, because I guess the difficulty you run into is that under the sort of hypothesis or one of the parameters is zero, then the optimization for the rest of them becomes different, right? So I think that like sort of, you know, perhaps obviously, but like the computational difficulty and sort of the I think most important area for next steps of research here is that, you know, this is all very nice when you have sort of finite, easily optimized models. But when you are trying to do something where the model space is, you know, more infinite or harder to optimize, then like because it's a Monte Carlo method like this, you can parallelize it perhaps, but it still becomes like computationally very expensive. And unlike Edwin's paper, where there's this sort of nice copula-based approach that gives you a very quick predictive update in the sort of parametric sense. You know, I mean, it's hard to write down a copula from model to model, so to speak, if that is even a concept that could exist. So so the sort of computational side of it is definitely like the biggest area for upcoming research. I think we have, you know, some sort of ideas that like you could do some sort of online updating where you don't fully re-optimize the thing from scratch every time, but you use some gradients, some approximations, something to sort of try and just slightly reshift your optimization as you go. Um, but I think that's very much sort of the big open question.
Cool. Thank you.
Maybe I'll wrap up with a last question. I mean, we still have time, so if there's anyone in the audience who wants to ask, they can start brewing the question now. So Vic, you mentioned that like you're using the BIC for kind of computational reasons. I guess the BIC is based on like the log likelihood. Is there a kind of way that that is used for the convergence proof? Like, is it the fact like do you need the model score to kind of depend or be really closely connected to the score function? I know Steven sometimes uses those to construct martingales, from what I remember. So I wonder if it applies in your context as well.
Like the convergence proof does sort of, yeah, rely on, the likelihood, um, like the likelihood converging as you would observe more and more data. And then the sort of complexity parameter is more general within that. But the BIC sort of is what we happen to use here because of its nice properties. Um, and I think there's, like in that variable selection example that I was mentioning earlier, for example, right? You see actually what you would sort of expect, that if you do it with the AIC, then you tend to pick models that are too complex, right? You tend to like leave way too many variables in the model. Whereas if you do it with the BIC, then you get that sort of implicit regularization. But the convergence or the proof, so to speak, is it doesn't rely on that. It relies on, like you mentioned, the likelihood and then some penalty for the complexity. Yeah.
Okay, great.
Mhm.
So do we have any final questions in the chat or audience?
Can I have a question? Yeah, I'm
Yeah,
just
James here.
wondering. So you choose your best model and then you do the predictive sampling, if I understand correctly. Does it ever happen that the best model that you get at the end is different from the initial best model, or never happens?
Yeah, so perhaps I'm not understanding your question here, but here, for example, right? Or if we go back to the previous one, right? Something like this, right? So I
Right.
mean, in this case, your initial hypothesis is H1. I mean, you're always going to have one of the models being sort of the best one at the beginning. And if you were just to optimize with VIC and say I'm done, then that's what you would pick. Um, but you have several sort of sample paths that cross over into different models. And in
Okay.
the sort of density estimation example, right, same thing, where you have sort of every model sample path in that case began at one component, but then several of them sort of cross into other components because the introduction of the new data points is what propagates your uncertainty.
But at the end, you get the best model, which is the most likely, the one with highest posterior probability, right? At the end, you
Yeah.
get the best model as the
Okay.
one with highest posterior probability. Is is usually the
Right. I see
same
what you
as.
mean. No, 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 I see what you mean. I don't recall in any of the simulations I ran, I don't recall seeing that result. But yeah, I guess that we're sort of interested in the different posterior weights at the end rather than just picking one of them as the best. But no, I don't recall in the simulations that I've run seeing one where sort of the initial best model, at least in these sort of simple cases, didn't end up being the one with the highest posterior probability.
Okay. Okay. Thank you.
Okay, well, if there aren't any final questions in the talk, then we can thank Vik for his excellent talk. And we'll see you guys in another month-ish for the next section by Professor Lorenzo Capello. Thank you so much for attending, and thank you, Vik, for giving an excellent presentation.